Okay, so welcome to Chapter 5, Properties of Waves. So we just finished heat, and now we're going to transition into thinking about things in terms of waves. So in heat, we talked about collision theory, talking about how when particles are moving faster, what does that mean with relation to temperature and enthalpy. Now we're going to switch gears and focus on what a wave is. So we're really into the unit of physics here. And we start off by, and I'm assuming you've actually read through the notes here, so I'm going to go quickly through most of these slides and really just do one of the practice problems on slide 13. But I wanted to just point out a few things in the characteristics of waves and what makes them unique. Let me just switch colors here. So, waves transmit energy, waves travel through a medium. All this is pretty intuitive. Wave has to be started. Okay, you need a wave source. Here is a really interesting thing. What distinguishes a wave from a particle is something called principle of superposition, or that waves will pass through each other. This is much different than a particle. If particles are within the same trajectory, they will collide, okay, and then they'll deflect depending on their initial conditions. Waves are different. Waves will actually pass through each other. So if you send two sound waves at each other, okay, once again they'll pass through each other. You can notice this if you have a conversation with someone at the same time. Both people are talking, you can still hear them. Sound waves are passing through each other. It might be more difficult to hear because you have some what I guess you would call noise, but they can do this. And something that's you should also remember is this last point: the speed of a wave. Now, I'll just read it. The speed of a wave depends upon the type of medium the wave is moving through, and that's it. This is pretty counterintuitive. If you were to throw a baseball, and I was to ask you, what does the speed of the baseball depend on? You would say, the force or energy that is imparted into the ball through the person's arm. Perhaps you would talk about air resistance, but it doesn't really play a factor. In waves, no matter how aggressive the wave source, so in other words, if you say jump into a big pool of water from a small height, you're going to create some waves. If you jump from a large height, the speed of the waves you create, despite the fact that you're imparting a lot more energy, is actually independent of that. In other words, the speed won't change. It only depends on the medium. So what will change? Only the amplitude of the wave will change, okay? And the frequency of the wave will change. These two terms, amplitude, frequency, wavelength, we shall talk about right now. So in this section, there are two types of waves. Transverse waves are what we're typically going to deal with. And that's this guy right here. So if you take a slinky and you fling it upside down, or fling it up and down. Wavelength is the distance between two troughs. That's what these are called, lower points, or two crests. Okay, same distance. Longitudinal wave is a compression wave. So if you were to push horizontally, we're typically going to deal with these guys, but these ones can turn up now and then. Hopefully you've read through pulse waves. Let's get into some characteristics of transverse waves. So we talked about wavelength already. You can see it down here. Amplitude is the distance to the horizontal axis. Okay, so don't go down here at all. Okay, don't do that. Just that distance. Like I said, if you're to impart more energy into a wave source, or into the wave source, so for instance, in the slinky example, if you're to really become really aggressive with the slinky here, that extra energy will go right into the amplitude, and it might go up way higher. However, the velocity of the wave will be the same. So what is velocity equal to? Well, velocity is distance over time. Okay, the total distance over the total time. We're going to have a bit of an easier way of dealing with this in terms of using wavelength. But we'll get to that in point 4 actually. For the frequency of the wave, I mentioned frequency before. I mentioned amplitude and frequency. The frequency, by definition, is how many cycles or how many wavelengths pass by a certain point per second. So given this picture, if this duration is 1 second, how many wavelengths pass by? A wavelength is, remember, the distance between a crest and a crest and a trough and a trough, which you can see in this slide right here. Okay, here's a crest, that's a wavelength. Also important to note, though, that you can take any 2 points that are in phase and measure wavelength. Or by definition, 2 points that are wavelength apart are what we would say in phase. So for instance, if I went and picked this point, what's its corresponding point? This guy. Not him. Not there, because this point is going up and it's not a wavelength in distance. This one's going down, so is this one, and they're wavelength apart. So in other words, you can also measure this point and this point. That's one wavelength. When you look at this example over here, we have 1 wavelength, 2 wavelengths, 3 wavelengths. Therefore, we have 3 wavelengths passing by this point every second. Okay? So that is its frequency. It's 3 cycles per second. Now, we typically call a cycle per second a hertz or hertz. So in other words, this is 3 hertz. If you look at the back of any kind of electronic device that outputs sound or any kind of energy, like microwaves or something like that, X-rays, if you somehow happen to own an X-ray machine, if you go up to your microwave, look at the back, you'll see the frequency of the pulses of the waves that are generated on the back in hertz. Okay, and the higher that number is, the more intense or the faster your food will cook, essentially. So the period of a wave is basically time. It's not a very convenient unit, actually. It's the time required for a single wave to pass a given point. It is the inverse of frequency. So I'm assuming you've read this. If you're given frequency, you're basically given period. You have to go 1 over frequency to find it. If you're given period, you are given frequency indirectly, because F is equal to 1 over T. Make sure you copy that down as well. So here are some problems basically dealing with distance and time. Basically dealing with frequency and period. Read through those. Pretty straightforward. Now let's get to velocity. Velocity, of course, is distance over time. However, in wavelengths, in the terms of the wavelength, remember, wavelength is a distance. Because the velocity of a wave is actually basically constant in a medium, all you actually have to know to find the velocity of a wave is to look at how fast it moves over the span of 1 wavelength. Okay, this is slightly different than if you're to try to find the speed or velocity of someone running 200 meters. Okay, you would take the average speed in that case. Okay, so if you rearrange this according to wavelength, you actually are given this formula. Remember, period is basically time. So you have wavelength over time. This is a distance, so this is distance over time still. I'll put the time in brackets. But because period is 1 over frequency, you can rearrange it to get this lovely formula. Velocity is equal to wavelength times frequency, which is what I do in these examples. Finding velocity, you're given the frequency, you're given the wavelength. Here you're given the speed or velocity, and you're asked to find frequency given the wavelength, in which case you rearrange the formula. So I can get you to solve for any of the variables. Now, let's get to pendulums. Let's get to this practice problem at the end here. So a pendulum can be seen to be like a wave, actually. You can analyze pendulums like a wave. And the reason is because they actually follow the same sine or wave-like nature. You can plot them just like a sine wave, okay, because they swing, because they're periodic motion. Notice how all these waves are periodic, right? 1 wavelength, repeat, 1 wavelength, repeat, 1 wavelength. A periodic motion. Same thing with a pendulum. right? Swings here, goes back, swings back. That's one wavelength. In terms of if you were to plot this on the sine graph, the amplitude here is this. Okay, that's amplitude. The distance from the center point, or 0 degrees. So in other words, when it is out here, you could plot that to be at the peak here. That's its peak point. It comes back, it hits 0, comes back, hits 0, goes back this way, goes back underneath, comes back this way, hits the center point. That's one wavelength. It's important to note that in a pendulum it has to go 2 ways before it reaches go again, right? A wavelength is here, here, and then back to here. Just like a sine wave. When you keep that in mind, well, keep that in mind when we do this question here. A metronome is a device used to keep time for musicians. It clicks every time it passes the center. If a metronome clicks exactly 80 times in 20 seconds, what is its frequency and period? I picked this example to do in this video because you have to read the question closely. This is a metronome. Every time it passes, it clicks, which means it actually clicks. Remember, a wavelength is here and then back again. So we'll actually click twice. It clicks 2 times per wavelength, which means you're asked to find the frequency. Frequency is cycles per second. So remember, if you're ever wondering what frequency is, you always say to yourself, cycles per second. It's cycles per second. How many cycles are here? Not 80, actually 40 cycles, because it clicks twice per cycle. So you have 40 cycles over 20 seconds, which in this case is 2 cycles per second. In terms of significance, I say go to 2, so this is 2.0 hertz. Keep that in mind. So that actually wraps up our first section. There's only 3 sections here, but this one has the most problems associated with it. Master this little mantra here, cycles per second, that's what frequency is, and really master the practice problems in terms of velocity, wavelength, and frequency. When you're ready, move on to section 5.2.